In the first two videos, we focused on steady-state simulation and explained how to handle linear and nonlinear circuit elements. The circuit being simulated is assumed to have no time dependence, and the output is only dependent on the given input. That is, all the circuit elements have no memory, and the history of the circuit is ignored. In this video, we will discuss how to perform transient simulations with time-varying signals, and the elements of which the characteristics depend on some previous states. Starting from the circuit we used in the previous video, the current source IS5 will now change with time. But at each time point, it can be considered as a static current source with known value. In addition, a capacitor C6 is added as a new branch element. Following the given procedures to write the circuit equations, we start from the new branch equations, which are given here. The current source is simple, as it can be treated as a constant current source once the time is given. The current through the capacitor is given by the derivative of the charge stored at the capacitor with respect to time. For a linear capacitor, we can express it as the capacitance times the time derivative of the branch voltage. We have not learned how to handle it yet, and we will just leave it as is for the time being and move on. The next step is to write the KCL, and we only focus on node 2. After that, we apply the branch equations to the KCL and obtain the following equation. Finally, we replace the branch voltages with the node voltages by applying KVL. We have these final equations. Now, we have to handle the time derivative of the voltage, which is something new. As the current is actually controlled by the branch voltage, we keep the branch voltage for the time being for the derivatives to preserve the generality. Recall that the purpose of the branch equation is to estimate the branch current with a given branch voltage. Before doing that, let's look at what the simulator is doing in a graphical representation. Suppose the exact solution for the branch voltage to be reproduced is given here. As we are solving for numerical solutions, we do not have an analytical equation for it. The solutions will just be represented by some discrete sample solution points as shown here. We will solve each solution point one by one. At each solution point, we consider the behavior of the circuit to be the same as the steady-state case. When we try to solve for the solution at the ith time point that we denote as Ti, all the branch voltage from T0 to Ti-1 and their time derivatives have already been solved and can be considered as known constants. The simulator will perform iterations at time Ti. With an iterative guess for the branch voltage value, the currents will be given by the time derivative associated with the presented voltage at time Ti. Therefore, to calculate the branch current, it is the same as to find the time derivative of the branch voltage at time Ti. Remember, the problem of the simulator is how to calculate the iterative branch voltage and branch current at Ti consistently. To do that, we have to apply some numerical solution technique to solve differential equations. For a first-order differential equations, usually the derivative of the function is given, and we have to find the function. For the solution of the branch equations, we may assume that the branch voltage and its derivative at time equal to 0 to Ti-1 have been solved exactly. Then, after a time increment of Hi, what is the value of the branch voltage at Ti? The simplest approach is to estimate the branch voltage at Ti by using the branch voltage at Ti-1 plus its time derivative multiplied by the time step Hi, as shown in the figure. We can also write the corresponding equation here. In the equation, we use the dot on top of BV to denote the time derivative. This method is called the forward Euler integration. As shown in the figure, it will introduce an error in the approximation. But the error can be minimized by taking a small time step Hi. And the general form of the forward Euler equation is given here, after rearranging the terms. Besides using the time derivative at Ti-1, we can also use the derivative at Ti, which is assumed to be given explicitly. In this case, the branch voltage at Ti can be estimated by its value at Ti-1 plus its time derivative at Ti times the time increment. This method is called the backward Euler integration, and the corresponding equations is given here. As using both the derivatives at Ti-1 and Ti results in error in estimating the branch voltage at Ti, we can take average of the two derivatives and use it to estimate the branch voltage at Ti. This method is called the trapezoidal rule, and the equations is given here. In all three cases, we only use the branch voltage and its derivative at Ti-1 to estimate the solution at Ti. However, it is possible to use more previous solutions before Ti-1 to provide additional information when guessing the value at Ti. The general form of the equation is given here, where P represents the number of previous time points used to calculate the current solution. In the case when only one data point at Ti-1 is used, P is equal to 1. But higher value of P can be used to improve the stability in the simulation, which will be discussed in another video. There are also two different classes of numerical solutions depend on the value of beta 0. When beta 0 is 0, the branch voltage solution at Ti does not depend on the derivative at the current time point Ti. It is called an explicit method. When beta 0 is non-zero, the branch voltage solution at Ti will depend on its derivative at the current time point. It is called an implicit method. After describing the approach to find the solution of the differential equations, we will apply them to find the branch current. We will start from the forward Euler method. From the branch equations given here, we will apply the forward Euler equations. As the time derivative of the branch voltage is equal to the branch current divided by the capacitance, we replace the time derivative with the current. Here, the equation is relating the current at Ti-1 to the value of the branch voltages. To find the current at Ti, we have to make an extra increment to the time value. After rearranging term, we obtain the equation given here. So, to calculate the value at Ti, the future value of the branch Ti plus 1 is needed. It is not preferred. We can also use the backward Euler method to find the branch current. The equation from the backward Euler at Ti is given here. We then replace the time derivative of the branch voltage with the branch current divided by the capacitance. Then rearrange the terms, and we obtain an explicit expression of the branch current at Ti given here. It does not depend on the future value of the branch voltage, and the value of the branch voltage at Ti and Ti-1 will be subtracted by the simulator. With this branch equation, the nodal equation at node 2 we have earlier can be written as the following. And after using KVL to replace the branch voltage with node voltages, we have the following equation. In this equation, I include the term V minus at Ti to show its general form. In the example circuit here, V minus can be ignored as the negative terminal of the capacitor is connected to ground. We can rearrange the terms of the nodal equation at node 2 into the form given below. We notice that the part in the middle is contributed by other branches, unrelated to the capacitor. The contribution of the capacitor are highlighted in red. For the left-hand side, it is just like the contribution of a resistor with the conductance equal to C6 divided by Hi. And the right-hand side is just a constant, because all the values at Ti minus 1 are known and will not change in the iteration process. So the right-hand side is just like a constant current source. Using the concept of resistor and constant current source, we can derive the matrix entries of the circuit matrix as shown here. Up to now, we have not discussed the value of Hi. The way to determine its value will be provided by another video. At this moment, you may just treat it as a value to be determined and provided by the simulator. The matrix entry also indicated that the capacitor can be treated as an equivalent circuit composed of a constant current source plus a resistor in parallel. And the values are known when performing iteration at time Ti. Then, all the simulation methodology given in the previous videos can be used. To start the iteration, an initial conditions of the branch voltage at T0 is needed. If this value is not provided, it will commonly be treated as 0. Instead of the backward Euler, we can also use the trapezoidal integration to find the solution. The equations of trapezoidal integration is given here. Replacing the time derivative of the branch voltage by the branch current, we can express the branch current at time Ti by the equation shown here. Applying the branch equation to the nodal equation at node 2, we obtain the following equation at time Ti. And we can apply KVL to convert the branch voltage to the node voltages. We get this equation here. After rearranging the terms, we can get the following equation. Similar to the backward Euler case, the middle part of the equations comes from other branches. The contribution of the capacitor to the left-hand side is just like a conductance times the node voltages. And the right-hand side is just a known constant, already evaluated at the previous time Ti minus 1. So, the contribution of the capacitor to the circuit matrix is just what is given here. And this can be regarded as the equivalent circuit of a current source in parallel with a conductance with the values given here. With the equivalent circuit, similar simulation process at what were given in the first two videos can be used to handle the contribution of a capacitor to the circuit. Among the three integration methods, the trapezoidal rule is considered to be the most accurate one, and it is the most widely used approach. After discussing how to handle capacitors, we now switch the focus to handle another time-dependent element, which is the inductor. Now, we replace the capacitor in the previous circuit with an inductor. The branch equations of the inductor is given here. We follow the same procedures to write the KCL at node 2. Then, we apply the branch equations to the KCL. And we use KVL to express the branch voltages in terms of the node voltages. We still keep the branch voltage for the inductor branch. Similar to the capacitor case, we have to find the explicit current versus voltage characteristics of branch 6. We will again start with the forward Euler integration method. The target function in this case is the current, and the derivative is the branch voltage, as shown in the figure here. Following the forward Euler equations, the current at time ti is given by this equation. The right-hand side consists of values at time t-1, which is just a constant. It can be regarded as a constant current source with an equivalent circuit given here, and its corresponding matrix entries are given here. Again, we need an initial condition at time t0 to start the simulation. We can also apply the backward Euler integration method, and the current is expressed by the equation here. The first term is from the ti-1 time point, and it is a known constant. The second term is equivalent to a conductance times the branch voltage at Ti under iteration. The equation can be represented by an equivalent circuit given here, and the corresponding matrix entries are shown here. Again, an initial condition at T0 is required to start the transient simulation. We can also use the trapezoidal rule method to perform the integration, and the equation is given here. After rearranging the terms, we can again come up with a conductance times the current iterative branch voltage plus a constant term. Based on the equation, we can construct an equivalent circuit at time ti as shown here, and the matrix entry at ti is given here. While the implementation of the branch equation for an inductor is quite straightforward, but in some cases, like mutual inductance, it is more desirable to treat the branch current as the state variable for iteration. Alternatively, we can transform the equivalent circuit of an inductor to its Thevenin's equivalence, which consists of a voltage source and a series resistor as shown in this figure. Treating the Thevenin's equivalence as just a single branch, we can write the branch current as what is given here. Applying KVL to convert the branch voltage to node voltages, we can see the contribution of the inductor to the given branch. The value of RLEQ and VLEQ depends on the integration method, which are derived before, and there are three state variables in the equation. Following how we handle a voltage source, the equivalent entries to the circuit matrix is given here. This approach is used in some early day spikes implementation to indicate inductor is a current control element. So far, we have discussed the way to handle linear capacitor and inductor. While practical inductors are usually linear in nature, a lot of capacitors we encountered are quite nonlinear. A simple example is the reverse bias PN junction capacitor. So, I will give a brief introduction on how to handle nonlinear capacitor here. I will come back to it when I discuss the development of capacitor models in the future. Recall that the branch equation for a capacitor current is given here. When C6 is a linear capacitor, we can rewrite it as the capacitance times the branch voltage. However, when the capacitor is nonlinear, the relationship of Q equal to CV no longer holds, and an explicit relationship of charge and branch voltage has to be derived. That is, an explicit QV relationship is needed. It implies that besides the IV relationship of the branch, a QV relationship is also needed with the charge as the state variable. Alternatively, we can apply chain rule to the branch equations and obtain the current in terms of its capacitance. But the capacitance is not a constant, and depends on the branch voltage. The model of the capacitor have to provide this relationship before circuit simulation is possible. I will discuss this in the future when I cover capacitance modeling.